Hello students. So welcome to my YouTube channel. So today I have come up with another chapter. So today we're going to start the new chapter in chemistry, which is ionic equilibrium. As you can see the heading on the board. So we're going to talk about the ionic equilibrium. This is a very important chapter for JEE students as well as for NEET students also, because you can expect at least one or two questions from this chapter. Like you can guarantee you can expect at least two questions from this chapter for NEET students. For JEE students, yes, you're gonna expect at least like one or two questions for sure. So in physical chemistry especially, this chapter is one of the most important chapter, you can say most important topic. So you cannot neglect this topic because this topic will decide your rank. Other, if I talk about other chapters, basically let's say solutions or let's say mole concepts and all, like you can find some easy questions there, you can solve those questions. But in ionic equilibrium especially, many of the students have a doubt, like they keep on asking, sir, this chapter is very tough, how to solve all the questions. So I have tried to simplify as much as possible. I have tried to make it easier for you. So you listen to my lecture carefully, you listen to my words, statements, everything carefully, and whatever I'm saying in the lecture, whatever I'm saying, you just note it down, copy it down, and listen twice, thrice. Practice as much as possible. Then you can have a command over this chapter. That's my guarantee. If you follow all the instructions, all the suggestions which I'm giving it to you, if you follow everything, you're gonna be master in this topic. So do not ignore this topic. Just focus on every statement, every word. And if you study properly, if you command on this topic, then there is high probability, high chance for you to get a good rank. Because other students also, they focus on the easiest topic, but sometimes they do not focus on the important topics, right? So that's why this is going to be very crucial. And so do not ignore even a single statement. Whatever I'm saying, just follow that properly, right? So let's start the session. So as you can see, the chapter is ionic equilibrium. So what we gonna study in this topic, what are we gonna study about this? So the first thing is, just like we studied in the chemical equilibrium, we know that every reaction achieves equilibrium. No reactions like get completed 100%. Every reaction achieves equilibrium. What is the meaning of equilibrium? We are talking about the dynamic equilibrium, not the static equilibrium. Dynamic equilibrium, what does it mean? The rate of forward reaction, the rate of reaction in the forward direction is equal to the rate of reaction in the backward direction. Rate of forward direction is equal to rate of backward direction. That moment, the moment when the reaction achieves this state, we say that the equilibrium has achieved, right? So in chemical equilibrium, we spoke about like other reactions, basically molecular reactions, or you can say other reactions where the dissociation or decomposition took place. But here in ionic equilibrium, we gonna talk about ions. For example, let's say if I write acid, let's say HCl. If I write HCl, then if you dissolve in water, if you add in water, this HCl will dissociate into H plus and Cl minus. This will dissociate. Now this reaction will also achieve equilibrium. We will talk about each and every segment. If I talk about, let's say, NH4OH base, if you again add water, if you add water in it, this will again dissociate into NH4 plus OH minus in aqueous. This is going to happen. What I mean to say, this reaction will also achieve equilibrium. So in this topic, we are getting ions, right? We are getting ions. And so we're going to talk about the ions especially. So what is the motive behind studying this chapter is we're going to talk about ions. Now if you get, let's say if you get H plus ion, then you know very well, when you get H plus ion, concentration of H plus ion, then the substance becomes acidic. It shows acidic nature. If you get a concentration of OH minus ion, you say that the substance is basic in nature, right? So when you get H plus or when you get OH minus, you calculate the pH. You might have studied in class 9th or 10th, like the pH, something which is acidic, the pH is lesser than 7, something the pH is something is basic, the pH is greater than 7, which you have studied, right? Little bit of this you have studied, so you may have some bit of idea. So that means if you get a concentration of H plus or if you get a concentration of OH minus, which means you can comment whether the substance is acidic or basic in nature. And when you comment whether the substance is acidic or basic, basically you calculate the pH, right? So that means we gonna talk about the pH of a given solution. So that's the first, you can say, the first objective of this chapter, the first objective. Because if you follow my lectures, I have explained everything. Whenever I begin with the chapter, I explain everything, like what are we going to study in that topic, what are we going to study. So that's why it is very crucial, very important for us to understand, like what are we going to study in this topic. So the first thing is we're going to talk about pH calculation of a solution, right? Now, second thing, after pH calculation, what else? So you might have studied like the titration process in mole concept, like normality N1 V1 is equal to N2 V2, right? So we used to study about the redox titration there. So in the titration process, we use different type of indicators. Now, what are indicators? Indicators are something which helps us to decide whether the solution is acidic or basic in nature. That's what they help us to decide. So which type of indicator we are going to use in which type of like titrations? So what I mean to say, for different type of titrations, we use different type of indicators. And which indicator will be like better for us to use for a particular reaction? That's what also we're going to study in this topic. So we can say indicator, the type of indicators in the titration process, different type of indicators in different titrations. That is the second objective. Second, the third objective, basically. The third objective, you can say that like many salts, if I talk about the salts, most of the salts dissolve in water, but there are so many salts which do not dissolve in water. They dissolve partially, like very slightly they dissolve. They don't dissolve like 100%. Some salts are there. So like we will study how much the salts can dissolve and how can we increase the solubility of a salt. So let's summarize this, what I talked about. So basically we're going to study about the pH calculation of the given solution, the indicator used in different titration process, and the third thing is the solubility of a given salt. So these are the three objectives, these are the three things which we're gonna study in this chapter. This is very important. So you can start writing, you can write it, that the like objective of this chapter. So you write, this chapter deals with the, okay, you can write, this chapter deals with the the first point, pH calculation, pH calculation of a solution, pH calculation of a solution. The second point is, after that, uh, indicators used in different titrations, right? And the third thing which I said is the solubility of a salt. solubility of a salt, right? Write it properly, because each and everything is very important. So do not miss out, do not skip anything. Just whatever I have explained you, just follow that properly. Like write the explanation part also, because that will help you to understand the chapter in a much better way, right? So I hope you have written. So now we will discuss as per this thing, as per this sequence. First we will discuss about the pH calculation of the solution. But to understand this topic, to understand this concept, we need to understand few more things. So let's start the first thing. So before that, we need to understand some important terms. And the first term is electrolyte. So you can write the heading electrolyte. Okay, so I'm erasing it. Electrolyte. Now, like you may have a question. What is an electrolyte? Electrolytes are basically the ionic compounds which conduct electricity in the aqueous state or in the molten state. Molten means like in the water form, like uh, associated with the water, you can say. So I'm writing the definition. What are electrolytes? Electrolytes are these are the ionic compounds. These are the ionic compounds, or you can say which have or you can say which have ionic character, or you can say which have ionic character. Like some compounds, those are not ionic compounds, but these are also electrolytes, because they have ionic character, polar character, basically what I mean to say, polar nature. So these are the ionic compounds which have ionic character. Okay, these are the ionic compounds, or which have or which have or which have ionic character. Yeah, so these are ionic compounds which conducts electricity in aqueous form or in molten form. Molten means like you have just added few droplets of water. Molten form. These are called electrolytes. So you can add one more important line, that electrolytes dissociate into ions, into their like respective ions when dissolved in water. This is a very important thing. That means we are getting ions, and these ions are responsible for conduction of electricity. And like when will we get these ions? In presence of water. Basically you can say in presence of a polar solvent. Basically we getting ions in presence of a polar solvent. Now the question is, uh, like if we don't take the solvent, if we don't take the water, then if we don't take a solvent, then no dissociation will take place. And if no dissociation takes place, then you can say these will not act as a conductor, these will not act as an electrolyte, they will not conduct electricity basically. So that means we need solvent, polar solvent. And this entire chapter, in this entire ionic equilibrium, we are talking about water as a solvent. We don't have to, we just have to understand, like if we take another solvent, then what will happen, that we have to consider. But we just have to understand what will be the effect of other solvents. But we don't have to study about any other solvent, we just have to study about water only as a solvent. So that's very crucial thing. right? So now we have three different type of electrolytes. You can say electrolytes are of three types. Okay, the first electrolyte is we say it's a strong electrolyte. Strong electrolyte. The second electrolyte is a weak electrolyte. We have categorized. And how do we have categorized? Based on their dissociation into ions. Based on their dissociation, we have categorized into three categories. One is strong electrolyte, another is weak electrolyte, and the third is non-electrolyte. Now what does it mean? So if any electrolyte which dissociates 100% into ions, for example strong acids like HCl, it completely dissociates into H plus, and let's say if I talk about HCl, then completely into H plus and Cl minus in aqueous state. So completely dissociation of HCl takes place. So when complete dissociation of uh, an electrolyte takes place, we categorize them into strong electrolyte. So we can say, or you can say that, like for a strong electrolyte, the degree of ionization is 1, or you can say, or 100%. 100%. Right? So what is alpha? Alpha is our degree of ionization. I'm writing here. Alpha is degree. Just like in chemical equilibrium, we have studied about alpha is the degree of dissociation. In the same way here, alpha is the degree of ionization. We will talk about each and everything. So strong electrolytes where alpha is equal to 1. Weak electrolyte where alpha is greater than 0. Alpha is greater than 0 but less than 1, or you can say less than 100%. And here non-electrolyte means alpha is equal to 0, means no ionization takes place, no dissociation into ions, no ion formations. So we will talk about the examples also, right? So you can say in a strong electrolyte, all you can say all strong acids, or all strong base, and all type of salts, all types of salts. Okay, these come under strong electrolyte. Strong acids, you may ask like, sir, please give me some examples of strong acid. Yes, HCl, HClO4, HBr, Hi, these are categorized under strong acids. H2SO4, sulfuric acid, this is also a strong acid. Then further strong base, sodium hydroxide, NaOH, KOH, cesium hydroxide, calcium hydroxide, these are strong base. Salts, if I talk about salts, and then we can say NaCl, KCl, NH4Cl, ammonium chloride. Then if I talk about ammonium cyanide, these all are all like type of salts. So they dissociate completely into ions. The 100% dissociation takes place. You can write all those examples. If I talk about weak electrolytes, so what else remaining? So strong acids we have covered here, strong base we have covered here, all type of salts we have covered here. So what is left out? Weak acid and weak base. Yes or no? Say yes or no. I hope the point is clear. Weak acid example, CH3COOH, CH3COOH. Okay, let me just check whether it's being recorded. It is coming in the camera, right? Yeah, it's coming in the camera. So I'll write here CH3COOH, then HCN, it's a weak acid. Formic acid, all organic acids are considered as a weak acid. Then what else? Yeah, benzoic acid. Then if I talk about base, yes, NH4OH, ammonium hydroxide. This is a strong, weak base. Yes, we will like I'll give you more examples, but as of now these are sufficient. Like when I will discuss, I'll tell you one more thing, important thing. uh, so far as of now, you may have studied like something, some substance which dissociates into H plus in water. When they give H plus in water, these are called as acid. Some things which give OH minus in water, these are called as base. But later on in this chapter only, like as we move further, we will study different type of acid base theories. We will study three type of theories to define acid and to define base. There I'll give you more examples because there are so many examples of acids and base. So that thing is very, very important. So yes, in the upcoming lecture, I'm gonna give you more examples, but as of now, memorize all these examples. Remember all these examples. These are categorized as weak acid and weak base. Here, these are categorized as strong acid and strong base and all type of salts. These are strong electrolytes. These are weak electrolytes. And for if I talk about the non-electrolyte, yes, the examples are uh, glucose. Glucose. By the way, what is the molar mass of glucose? The formula is C6H12O6. Molar mass is 180. If I talk about urea, NH2CONH2, molar mass is 60. If I talk about sucrose, C12H22O11, C12H22O11, and the molar mass will be 342, right? So if you memorize this molar mass, that will help you to save the time also sometimes, right? So these do not dissociate into ions. They dissolve in water, that's true, but they do not dissociate into ions. So that's why these are not categorized as electrolyte, these are categorized as non-electrolytes. So we have to mention about the solvent which you're talking about, right? One more important thing, we if I have like described that these are the strong electrolytes, these are electrolytes in presence of water. In H2O, these are strong electrolytes. But if you change the solvent, they may not dissociate completely. If you take alcohol, alcohol is also a polar solvent, but when you take alcohol, they will not dissociate into ions completely, 100% no dissociation. In that case, they will not be considered as a strong electrolyte. So yes, if we are defining something strong electrolyte, so we are defining with respect to the solvent, and here we are talking about water as a solvent. I hope the points are clear. Let me briefly summarize. In this chapter, we're going to talk about the pH calculation, then the different type of indicators and the solubility, right? And I started with the electrolytes. What are electrolytes? The compounds which have ionic character, which conducts electricity in the molten state or in the aqueous form, and they dissociate into ions in the water when dissolved in the water. So we have three types of electrolytes: strong electrolyte, weak electrolyte, and non-electrolyte. Right? You can take the screenshot. Right? Yes. Now, shall I erase it? Right. All right. So, right. So far we have studied about the type of electrolytes. Now we're going to talk about Arrhenius theory of, you can say, dilution. So you can write the heading Arrhenius Arrhenius theory of equilibrium. Right? What does it say? The Arrhenius theory says that there exists a dynamic equilibrium between the ionized and unionized substance for a given ionic solution. What did I say? I said there exists a dynamic equilibrium. There exists a dynamic equilibrium between the ionized and unionized substance in a given ionic solution. Right? So first of all, I'll write the definition and then I will explain further. So what does it say? There exists a dynamic equilibrium. There exists a dynamic equilibrium between the ionized and unionized substance, okay, in a given solution, given electrolytic solution. Sorry. Or you can write in a given solution containing electrolytes. Okay, what does it mean? So let's say if I have something AB, okay, let's say if I have something AB, or I'm taking some HA, okay, I'm taking, let's say, HA. I have taken acid only for your reference. I have taken any acid, okay. I have added water because obviously we are talking about solution. So for solution we need a solvent. So which type of solvent talking about? We're talking about water as a solvent. So when you add the electrolyte in the solvent, make a solution, then this will dissociate into ions, as I have said. So you are getting H plus aqueous plus A minus aqueous. That's what the Arrhenius theory says, that there exists a dynamic equilibrium. Between the ionized and unionized substance in a given solution. Ionized and unionized substance, there exists a dynamic equilibrium. So they have achieved equilibrium, and this is what we're gonna study in the entire chapter. So now, so initially, let's suppose at time t is equal to 0, initially its concentration, let's say its concentration was C, right? Its concentration was C, and initially its concentration was 0, because for at time t equals to 0, the reaction hasn't started. Now at time t equals to t, the equilibrium has achieved. So I'm writing equilibrium has achieved. When the equilibrium achieves, so the concentration, like the final concentration at equilibrium, it will be how much? C minus C alpha, where alpha is the degree of ionization. How much it will form? C alpha and C alpha, right? So you write the equilibrium constant expression. So you will say K is equal to, for the given reaction, let's say equilibrium constant, K equilibrium is the equilibrium constant, which is equal to concentration of H plus into concentration of A minus aqueous divided by concentration of HA. Can I write like this or not? And you substitute the value. So you will get C alpha into C1 minus alpha. C gets cancelled. So you get C alpha square upon 1 minus alpha. Right? So this is what you get. And since we are talking about what? We are talking about acid. We are talking about acid. So the K equilibrium here, it is called as acid dissociation constant. So this K equilibrium will be called as acid dissociation constant. Means this is equal to Ka, which is equal to C alpha square upon 1 minus alpha. For this type of equation, for such type of equation, we are getting this Ka. So for your convenience, I am writing what is Ka. Ka is acid dissociation constant, correct? Or you can remember, when acid like is added in water, then the equilibrium constant is called as Ka. What did I say? I said when the acid is dissolved in water, the equilibrium constant is known as Ka. What if the base is dissolved in water? When the base is dissolved in water, the equilibrium constant will be called as Kb. And what will be the Kb name? I mean full form. It will be base dissociation constant. Just like you have calculated for acid, can you calculate for base in the same way? Yes, if you can. I'm giving you the equation. Let's say you can write for base, you can, what else you can write? Okay, shall I erase it by the way? Take the screenshot. Yeah, so let's erase this. So if I write base, BOH, aqueous, then what will you get? B plus aqueous, OH minus aqueous. Same, the concentration initially was C 0 0, at equilibrium C minus C alpha, C alpha. So K, so here the expression will change simply. It will be B plus OH minus upon concentration of BOH, and the symbol here, it will be changed, it will be Kb, right? Same way you can calculate. Yeah, so you have understood the Arrhenius theory, Arrhenius concept here. Now one important thing, just focus here. Look at the equilibrium constant. Let's write K equilibrium only. That is equal to, what is the expression we are getting? C alpha square 1 minus alpha, right? Now listen carefully. If you change the concentration, if you increase the concentration, what will happen? If you increase the concentration of the acid or any substance or of any base, if you increase the concentration, then this K equilibrium, will it change? No. You must have studied in the chemical equilibrium. On changing the concentration, equilibrium constant does not change. The equilibrium constant depends only on temperature. If you change the temperature, then it will change, otherwise this will not change. So what will happen? Let's say if you have increased this term, you have changed the concentration term, so the net effect should not change. I mean, this thing should not change. For that, what will you have to do? Since you have disturbed this value, you have disturbed its C value. So if you want this thing to remain unchanged, you also have to change this thing. You have to also change the alpha value, so that the net change in this thing is 0, and hence this should not change. Are you getting my point? So if you increase the concentration, if you're increasing, alpha has to decrease, so that the net effect should be 0. Means there should not be net change. So if you increase the concentration, the degree of ionization decreases. If concentration increases, alpha decreases. Or you can say that if concentration decreases, that means alpha increases. Yes or no? If you decrease the concentration, you have to increase the alpha so that the equilibrium constant value should not change. So if you decrease concentration, alpha will increase. Or you can say the same thing in a different way. You can say on dilution. So what happens on dilution? Concentration decreases, therefore alpha increases. And this is what known as Ostwald's dilution law. This is known as Ostwald's dilution law, right? So you can write up to here whatever I have explained. Just take the screenshot, right? So yes, so you can write the heading Ostwald's dilution law. So you can write Ostwald's dilution law. It says that on dilution, alpha increases, means concentration decreases, so alpha increases. And this is a very important thing, so do not miss it out. Memorize this. If you increase dilution, if you increase the volume, right, of the solution, the concentration decreases, then the degree of ionization increases, right? So we have covered a small segment here. So to move further, first we have to understand the alpha, how, like, on what factors alpha depends, right? How alpha changes. So you can write the heading factors affecting alpha. Factors affecting alpha. We will cover up this part first of all. We will finish up the alpha part and then we will move on to the solvent segment. So you can write factors affecting alpha. Like alpha depends on which parameters, right? Alpha means degree of ionization. So what do you think? So alpha depends, the first you can say the nature of the solvent. First, type of substance you can write. Types of substance, right? Now it's a very like practical thing, no? Observe phenomena. Whatever the type of the type of electrolyte you will take, that will dissociate accordingly. If you're taking HCl, which is a strong electrolyte, that will 100% ionize. But if you take a weak electrolyte, let's say acetic acid, so acetic acid will dissociate partially, will ionize partially. So that's very like each substance has a different extent of dissociation. I'll give a very simple example. Each student has a different, you can say, extent of understanding. Some student can like sit for 5 hours continuously he can study, he or she can study continuously for 5 6 hours. But some students get tired within 3 hours 2 hours. Some students even get tired within 1 hour. They are not able to concentrate even properly for 1 hour also. So that depends, no, student to student. I'm just giving a practical, like very common example. This may have happened with you also, right? You must have experienced someone is studying for like continuously for 5 hours 6 hours, someone is studying just for 2 hours. So that depends on person to person. In the same way, the type of substance, like how much it will dissociate, that depends on the type of the substance, right? So you can say the type of substance is the first criteria, like on which the alpha depends, right? So strong electrolytes dissociate completely, weak electrolytes dissociate partially. Then the second factor, the nature of the solvent. Nature of the solvent. Solvent plays a very important role in dissociation. So basically what happens, solvent, let's say if I talk about NaCl, let's say if I talk about NaCl, when NaCl is dissolved in water, the polar part of oxygen, like water, the oxygen which has a negative charge, that attracts the positive part of NaCl. So NaCl will have a positive charge, Cl minus will have a negative charge, water will have H2O, like the structure is something like this. So H2 has a partial, hydrogen has a positive charge, oxygen has a negative charge. So this positive charge will be attracted, this will be pulled by oxygen of water. Are you getting my point? This is being pulled by. In the same way, the chloride ion, which is having negative charge, this is pulled by hydrogen of water. Pulled by hydrogen of water. And then they dissociate. Like they will start breaking into ions. And further, in the end, they dissociate completely into ions. But if you take a different solvent, the dissociation will will not happen completely, you can say. So the dissociation depends on the solvent. Now each solvent has a unique property, and that unique property is known as the dielectric constant, which you may have studied in electrostats, right? What is dielectric constant? The dielectric constant is the tendency of a solvent to break the substance, to break the polar substance into ions, to dissociate or to separate them into ions. That property is known as the dielectric constant. So you can say uh, right in that way, that different solvents have different dielectric constants, different dielectric constants. Mode is the dielectric constant, right? Mode is the dielectric constants. Mode is the dielectric constant. Mode will be extent of what? Ionization. Or you can say mode will be alpha. Mode will be the extent of ionization. This was the second point. Now the third factor, the temperature. We know that these reactions, the dissociation of ionic, or the, you can say, electrolytes into ions, the dissociation of electrolytes into ions, basically it's an endothermic reaction. How it is an endothermic reaction, we will talk later on. So these are endothermic reactions. So when you increase the temperature, as per the Le-Chatelier's principle, the reaction will shift into the forward direction, means more substance will break into ions. If more substance breaks into ions, means alpha value increases. So yes, I'll tell you one more important thing, that in ionic equilibrium, you must revise, you must practice the Le-Chatelier's principle. You go through the Le-Chatelier's principle, because we gonna use Le-Chatelier's principle everywhere in ionic equilibrium. So you should understand, you should feel that what is Lee Chatter's principle. Few factors, like if you increase the concentration, if you decrease the concentration of reactants or products, if you increase the temperature, if you decrease the temperature, if you add inert gases and all. So you just read, you study all those things, you must remember that, because we are going to use it, and we study that in chemical equilibrium. So revise that part, then watch this lecture, just follow my instruction, then you will be able to understand properly, right? So as per the Lee Chatter's principle, as per the Lee Chatter's principle, the if you increase the temperature, the reaction will shift into the forward direction, means the alpha value increases. So since reactions are generally, since dissociation reactions are generally, since the reactions which you're gonna study in this chapter are endothermic, are generally endothermic, therefore as per Lee Chatter's principle, as per Chatler Lee Chatter's principle, increase in temperature, increase in temperature increases alpha, increases alpha, right? These were the three factors. We have two more factors, so just take the screenshot, right? I hope you must have written this. Then we have the fourth point, that is very important, which is common ion effect, right? Common ion effect, the fourth factor. Fourth factor. Fourth factor, which is the common ion effect. Fourth factor. Now you may have a question, what is common ion effect? You can understand with the name itself, common ion. It means very simple meaning, just listen carefully. Let's say you are adding a substance in water and the substance is getting dissociated into ions. So if you add those ions from the out source, means if you're adding those ions from outside, then the extent of reaction decreases. This effect is known as common ion effect. Let's say, just first of all I'll give the example. Let's say you are adding AB. Let's say it's a salt. Okay. Now AB dissolves into water and dissociates into ions A plus and B minus, let's say. Okay. But when you add this B minus, let's say if you're adding this from other source, from other container, you can say, you took some B minus ion and you added in the solution. When you added in the solution, then the extent of reaction decreases. Why does it happen? Because as per the Lee Chatter's principle, you are increasing the, we can say that as per Lee Chatter's principle, we can say that you are increasing the concentration of the product side. Yes or no? You are increasing the concentration of the product side. Any of them you are increasing. And when you increase the concentration of product, the reaction shifts in the backward direction. And when the reaction shifts in the backward direction, means the extent of dissociation, the extent of ionization decreases. Yes or no? That's what happens, and this effect is known as common ion effect. Understood? Let's understand one more time. This AB was being dissociated into A plus and B minus, and you, what you did, you added B minus from the other source. From somewhere you added B minus in the solution. Now the B minus concentration has increased from the expected value. The expectation were something different, but now it is like more than the expected value. So it may disturb the equilibrium, yes or no? So to balance that equilibrium, the reaction shifts in the backward direction, which means if the reaction is shifting in the backward direction, the extent of dissociation, extent of ionization decreases or not? Yes, it decreases. This effect is known as common ion effect. So I'm writing the definition first of all, and we'll explain further with the help of another examples. So you can say, what is common ion effect? If you add product from other source in a given solution, if you add product from other source in a given solution, in a given solution, then the extent of ionization or reaction, you can say extent of reaction, also you can say decreases. The extent of reaction decreases. This effect is called common ion effect. Common ion effect, right? So let's say we have two container. To understand this in a much better way, I have made two container. This is container 1 and here the container 2, right? We have taken two different container. Now let's say we have something BA. I added water in it. It dissociates into B plus, let's say, and A minus. Let's say it dissociates into B plus and A minus. Correct? Initially at time t equals to 0, the reaction, I mean the ionization has not started. So you can say its concentration, let's say C, its concentration was 0, 0. Or you can say, let's say, you can say C moles were there and the volume of the solution is 1 liter. Let's say volume of solution, let's say 1 liter, and C moles were there, correct? So initially it's 0, but the equilibrium achieves at some time t, the equilibrium has achieved. So let's say X moles have been consumed. How much it will form? X and X, right? So the K equilibrium constant will be equal to how much? X into X upon C minus X. Since the volume is 1, so moles or molarity will be same. Moles or the molarity will be same when the volume I'm considering 1 liter, right? So this is the expression. But now what you did, you added, let's say you added A minus from some other source. So again you write the same reaction, B aqueous. You will get B plus aqueous plus A minus aqueous. So at time t equals to 0, it has C moles. Again I'm talking about solution's volume is 1 liter, right? So again, yeah, so it had C moles. Okay, this reaction was not started, so its mole were 0, but you had added this from other source. You had added this from other source. So initially A minus will be present or not? Say yes or no. Yes. So let's say you have added A moles. How much you have added? A moles from other source, from somewhere you added. So A minus A moles is initially present. Now the reaction will take place at time t equal to t. Equilibrium will be achieved, and then dissociation, let's say y. So how much it will form? Y, and total concentration will be A plus Y, right? So equilibrium constant will be equal to Y into A plus Y upon C minus Y. Now you tell me one thing, compare both of them. Since, as I said, this thing is only temperature dependent. That means here also this should not change, both should not change. If equilibrium constant should not change, that means this value should be equal to this value. Yes or no? Now, if you compare them together, you will see this value has what? Increased. The numerator has increased. Here nothing has happened, but here the numerator has increased because you're adding something A. If the numerator is increasing, then this term has to increase or not comparatively. This term has to increase so that the net effect should get cancelled out. So C minus Y has increased. If C minus Y has, the difference has increased, what does it mean? Here C minus X, if you compare this and this, so you are saying this value has increased. Why it is increasing? That means this value Y is smaller than X. Compare, I said this value is bigger, C minus Y is bigger. That means the difference is bigger, means this thing has to be smaller, no? Let's suppose the C, let's say 10. For example, you take it 10. I said this has increased. So let's say Y value is 5. Here, let's say X value is 6. 10 minus 6, how much you getting? 4. 10 minus 5, how much you getting? 5. Difference is increasing, right? That means this proves that Y is smaller than X. That means the extent of dissociation has decreased. Understood? So wherever there is a common ion effect, the extent of ionization decreases. Understood? So repeat along with me. Say, whenever there is a common ion effect, the extent of reaction decreases. Wherever there is a common ion effect, the extent of ionization or reaction decreases. Repeat, just memorize this. Whenever there is a common ion effect, the extent of reaction decreases. So in that case, X is greater than Y. So remember this thing in your brain, in your mind. You should have this picture in your mind. Whenever you solve the questions ahead, you should have a picture. Whenever I say the word common ion effect, you should imagine this. Whenever I say the word common ion effect, you must imagine this. Then you will be able to understand further. Okay, the last point, the fifth point, that is concentration. So I'm erasing it. Okay, you can take the screenshot. Yeah. The fifth and the factor, fifth factor, concentration. I have already explained this concentration. Ostwald's dilution, already explained. Concentration increases, alpha, that is degree of ionization, decreases, concentration decreases, alpha increases. basically Ostwald's dilution law. If you increase dilution means on dilution alpha increases, right? So these were these 5 factors on which alpha depends, and we have successfully covered the alpha, and now we will talk about the the solvent. We'll talk about the water, and we will see all the conditions of water, what happens with water and all, what are the things related with water, how water is going to help us. So these all things, and pH calculation further, all these things we will discuss in the next lecture. So this is all for the first lecture. Just revise, watch twice, thrice. That's going to help you for sure. So thank you very much. So we will meet in the next lecture then. Thank you.